All right, yep, we're in the home stretch here, and thanks for everyone's attention on a Monday morning. This is a lot of material and a lot of math. So I'm going to talk about fluoridation for the last session. And okay. All right, I'm going to just go through what is fluoride, some of the public health issues surrounding fluoride, the three main fluoride compounds that we use in water treatment, some storage and handling best practices, some common feeders that we see in our water plants. We're going to go through some calculations again to determine dosages at the end. I'm going to talk about some lab equipment that helps us test residuals in the water, and then briefly touch on some reporting requirements. Okay, so what's fluoride? Fluoride is the ion form of fluorine, which if you can see in the top right-hand corner, that's circled fluorine. Fluorine is a gaseous halogen. It's estimated to be the 13th most abundant element in the Earth's crust and is widely dispersed in nature, almost entirely in the form of fluorides. So in groundwater, the groundwater will move through rock and sediment, where it will pick up other elements such as sodium, calcium carbonate, arsenic, fluorides, and other trace minerals. So you're probably familiar with the term hard water, and that refers to water that has a higher concentration of those dissolved minerals. And while some of the dissolved minerals, such as arsenic, can be harmful, or an excess of an element like copper can cause problems, many of the trace minerals are helpful building blocks for our bodies, such as iodine, iron, manganese, zinc, and fluoride. In groundwater, we can see fluoride levels ranging from barely detectable to over 10 parts per million. In salt water, it tends to stay fairly consistent, mainly because salt water is not picking up all those minerals underground, and we'll see saltwater concentrations around 1.2 to 1.4 parts per million. So this map just shows the regions around the world which have high fluoride, natural fluoride in their groundwater. So the areas in pink have groundwater with fluoride concentrations above 1.5 parts per million or milligrams per liter. They're the same thing. So you can see the western part of the US has a lot of natural fluoride in their groundwater. That central part of Mexico, southern part of the South American continent, is that Argentina? Yep. And then we see northern China, or just parts of China, and India also have a lot of natural fluoridated groundwater. Okay, so how did we discover fluoride's benefits for our teeth? Well, it started with this Colorado brown stain incident. There was a dentist on the right here. His name's Dr. Frederick McKay. He settled in Colorado Springs, Colorado in 1901. And as he was examining kids in the area, he saw a consistent brown mottled stain on their teeth, which we now call fluorosis. The stain couldn't be removed by buffing or polishing. It was actually part of the tooth structure, which led Dr. McKay to believe that the only way it could get there would be when the tooth was forming. Dr. McKay was originally from Philadelphia, so he was used to seeing infections, or patients with infections with decayed and missing teeth. But he realized that these patients in Colorado Springs had relatively healthy teeth despite the staining. So he began to study the question, but 30 years of research didn't get him much closer to an answer until he happened to visit the Ozarks. The young children in that area were developing the brown stain after a new water source had been tapped. So Dr. McKay started working with a chemist in Philadelphia and sent him water samples. Apparently, the chemist at first accused McKay of contaminating the samples, but after verifying the sampling technique, he discovered that all the water samples did contain high levels of fluoride. After a few more years and lots of testing, they found that fluoride levels of 1 parts per million did not cause the staining or fluorosis, but still seemed to prevent cavities. So the newly formed U.S. National Institute of Health then conducted a large-scale 15-year experiment in Grand Rapids, Michigan. And it was to start with the addition of fluoride compound to the drinking water January 1st of 1945. So within 11 years of that study, they found that the cavity rates in children dropped 60%, and the U.S. Public Health Service went on to make fluoride addition a public health policy by 1951. Okay, so why does fluoride benefit our teeth? Why is it needed? Well, the simple answer is acid erosion. And our teeth are basically bones with a hard enamel cover. And this cover is under constant attack from the things we eat and drink. So the high acid foods and beverages we consume, along with bacteria in our mouth, creates pits, crevices, and holes in our teeth. So if you look at this chart, things with a lower pH are acidic, less than 7, and includes lemons, vinegar, tomatoes. 7 is neutral, and then anything above 7 is more alkaline with a higher pH. So things with the lower pH that are acidic are attacking our teeth every day. So how does fluoride work to protect our teeth? Well, on the left here, we have a picture of tooth enamel taken at a very high resolution with an electron microscope. And the enamel surface on the left has been damaged and demineralized, which can cause which can be caused by poor dental hygiene, sugary or acidic foods, especially things like pop and coffee, and hard foods like candy or ice cubes. The tooth on the right has fewer holes because the fluoride compounds have bonded with the enamel and covered the damage. One of the bonds of fluoride is with calcium and calcium apatite. So since the covering of the tooth is an enamel matrix made from hydroxyapatite, fluoride is drawn to it. So it helps to fill in the gaps that are created before they can become worse. Many of the areas covered or repaired by the bond are stronger, and you can think of it as a drywall smackling smear coat. So one of the properties of fluoride is it acts as a shield for the enamel by remineralizing the tooth and strengthening areas that have eroded from pH imbalance. All right, so how do we use fluoride for our dental health? Well, we can get it topically through toothpaste and mouthwash with fluoride additives. Or if you have fluoride in your drinking water, you can get it systemically from your tap. You can also get fluoride through foods. So when fluoridated water is ingested, the fluoride ion seeks out and is deposited in the bone structure of the body. About 20% of the fluoride is incorporated onto the tooth surface while drinking the water. Most of the remaining fluoride passes through the stomach and is distributed throughout the skeletal structure, including the teeth. Incorporation of fluoride is most rapid during the time of the child's formation and growth. This time period is roughly from the 4th month of pregnancy to 10 years old. All right, well, of course, you can always have too much of a good thing, so there are some long-term, you could have long-term exposure to fluoride concentrations above 4 can cause osteosclerosis, calcification of the ligaments and tendons, and consolidation of the vertebra. Accidental ingestion of toxic overdoses generally cause vomiting, stomach cramps, and diarrhea. Fatal doses range from 4 to 5 grams, which is about 2,000 times the amount of fluoride swallowed by a person from a water supply. All right, just some quick Michigan statistics. This is 2019 data. See, this is just these. This is the percentage of Michigan residents on community water systems that have fluoridated water. So you can see that most of Southeast Michigan, 75 to 100% of Southeast Michigan has access to fluoridated water. You moved up to the UP, the Western UP, you can see that only up to 25% of those communities have access to fluoridated water. So in total, over 6.5 million residents, or about 89% of residents in Michigan have access to fluoridated drinking water. And additionally, 31.5% of residents have access to optimally fluoridated water, which is a level established by the CDC of 0.7 parts per million. All right. So just to summarize, the health benefits of fluoride. Fluoride makes teeth more resistant to tooth decay caused by bacteria. We typically see about 25% fewer cavities in communities with fluoridated water. Fluoride is proven to strengthen bones in the older population, reducing bone fractures. For every dollar spent on fluoride, it saves on average $20 on dental care. And fluoride costs cities between 50 cents to $3 per person per year. So optimal fluoride levels have no negative impacts. All right, just want to touch on optimal fluoride levels again. So the current optimal is 0.7 milligrams per liter with a range of 0.6 to 0.8. The maximum contaminant level for fluoride was initially established at twice the optimum concentration and was based on the potential for staining of the teeth at these levels. However, because staining is only an aesthetic problem and not a health concern, the EPA revised the MCL to 4 parts per million. So that's the maximum contaminant level for fluoride 4. Fluoride does have a secondary MCL of 2. Secondary standards are for aesthetic considerations only. They're not health-based. And those include that staining or color and taste and odor. So these standards are not enforceable, those secondary standards, because they are not at levels that present a risk to human health. Okay, so what are the types of fluoride? So fluorine in its natural form will always try to form a compound with other elements, primarily calcium, which create these fluorspar crystals shown above. And when it's at your water treatment facility, it's typically in the form of a liquid in a huge tank. So that's that hydrofluorosilicic acid. And this liquid is called, or this straw colored, and it has a typical yield of 18.2 to 19.8% pure fluorine ion. All right, two other commonly used types of fluoride are in the powder form, and that is sodium fluorosilicate, sorry, sodium fluorosilicate, or sodium fluoride. And then the sodium fluoride is what we have in our toothpaste. So these are both powdered forms, and you can see that when they're delivered, they're about 98% pure. The sodium fluorosilicate yields about 59.4% fluorine ion. Sodium fluoride yields about 44.2% fluorine ion. Okay, so this is a good slide to pay attention to, especially for our calculations. So this is you get a bulk acid solution delivered to your plant. The solution is generally 22 to 25% of that hydrosilicic acid. So the remaining 75% is water. So of that 25%, you can see the green and red box. And if we break down their atomic weights, we get an atomic weight of hydrogen of 2, silicon atomic weight of 28. We have one of those. And then we have 6 fluorine ions. So we multiply the atomic weight by 6 to get 114. And if you add their atomic weights up, you get a total of 144. And of that 144, you can see the calculation down below. 114 divided by 144 is 79.1% of that compound is pure fluorine ion. So the total solution delivered to your plant is 25% of the compound. And then if we want to get to just the pure fluorine ion, we multiply that 25% by the 79% to get 19.8% pure fluorine ion in that acid solution. So if you see that number, the 19.8% in our calculations, can go back to this slide to understand where it came from. All right. Then this is a similar calculation determining the pure fluorine ion in the powdered form of sodium fluorosilicate. So again, we look at and the formula is not on here, but the formula for sodium fluorosilicate is Na2SiF6. So when we find the atomic weights on the periodic table, we multiply the sodium by 2, the Si by 1, and the fluorine ion by 6. And we come up with a total of 188 for that compound. 114 divided by 188 is about 60.6% fluorine ion in that compound. So the powder that would be delivered at the facility is about 98% pure. So you just take 98% of that 60.6, and that's going to yield, that powder is going to yield 59.4 pounds of pure fluorine ion, which is much higher than the liquid, which was 19.8. Okay, same for sodium fluoride. We look at the atomic weight. The formula for sodium fluoride is just NaF, so 1 Na and 1 F. The total weight of the compound is 42. 19, the fluoride atomic weight divided by 42 yields 45.2% weight of the compound is sodium fluoride. I'm sorry, is fluorine ion. Again, the powder delivered to your facility is typically 98% pure. So if you multiply 98% times 45.2, you'll get 44.2 pounds. Your powder will yield 44.2 pounds of pure fluorine ion. Okay. All right, just some fluoride storage and use best practices. So again, if you are applying any chemical to your drinking water, it has to meet NSF ANSI standard 60. Plants that accept large shipments of fluoride should feed from a day tank, and that's of course to prevent overfeeds because we don't want to exceed that maximum contaminant level of fluor out into the water that our customers are drinking. So we recommend day tanks for fluoride. It should be about 24-hour supply. Spill containment should be provided. Any feed points should be on the downstream side of a well check valve. And you should be able to isolate the fluoride feed when the plant is shut down. All right, of course, some fluoride safety things to keep in mind. So you should have that PPE handy for your operators, including gloves, aprons, a face shield, an eye wash. You should have a plan in place for fluoride spills. Hydrofluorosilicic acid will off gas and can be corrosive, often etching the glass of chemical rooms. Fluoride chemicals should be isolated from other chemicals inside of a building and vented to the outside. Now, an example is mixing of hydrofluorosilicic acid with sodium hypochlorite can cause catastrophic damage through extreme chemical oxidation and can also be toxic. All right, the injection into any pressurized pipe, the injection quill, as you can see from this photo, which is this should be in positioned at 5 or 7 o'clock to prevent corrosion from any leaks. So you can see that that injection quill is not at 5 or 7 o'clock and they're getting some corrosion. If injecting into a pressurized pipe, you need redundant anti-siphon valves. That's not required if you're injecting into an open basin. And then the electrical outlet must be wired so feed equipment is energized only when the well pump is energized. All right, just some types of feeders that we see in our water plants. So we'll have volumetric, delivers a certain volume of chemical. Gravimetric delivers a certain weight of chemical. Positive displacement pump, that's the most common in Michigan, and that is used with the hydrofluorosilicic acid, the liquid. Or you can have an upflow saturator, which is for that powder, and it's the safest. I'll talk a little bit more about these coming up here. So the volumetric, again, it's the volume of dry chemical is measured by the machine. And it's added to a solution tank, which you can see on the right here. It's mixed thoroughly and then delivered to the potable water supply. This is used primarily with the powder forms, and then primarily sodium fluorosilicate. It's fed by gravity. It's not pumped into the piping. It's very operator dependent. The equipment tends to be bulky and costly, and it's best at large water treatment plants with open basins and continuous oversight. The gravimetric feeders are very similar to the volumetric, just major differences. Instead of measuring a volume of chemical, we're measuring the weight by the machine. You can see there's two small scales. So that weight of fluoride is added to a solution tank and mixed thoroughly, and then fed into the treatment plant. Again, this is best at large water treatment plants with open basins and continuous oversight. Okay, then our most common setup is the positive displacement pump. So the fluoride is pumped out of a day tank and directly into the water system. And the day tank is typically on a scale for weight determinations. The day tank should also have overflow protection. And then you can see here, there's two anti-siphon valves. One's on the discharge side of the feed pump. And then one down here at the point of application. How are we doing on time? Okay, half an hour. And then the last type of feeder, this is an upflow saturator used for sodium fluoride. So you can see we have the saturated here. It's filled with sodium fluoride solid that's allowed to dissolve in makeup water. And that water will hold or saturate at 4% sodium fluoride. So the handling of the chemical is pretty minimal in this setup. The 4% solution is the least concentrated of the fluoride compounds. So the possibility of a dangerous overfeed is reduced. The makeup water does need to be softened to minimize calcium deposits, but these saturators tend to be easy to operate. They eliminate the need for weighing the fluoride and eliminates any stirring needed to dissolve the fluoride. So, but I don't typically see these at my water plants. Okay, so fluoride testing frequency, pretty much the same for groundwater or surface water supplies. So minimum, we want to see monthly raw water samples collected. And then at the plant tap, you need to collect a daily fluoride sample. And then in the distribution system, you want to collect those fluoride samples weekly. And all of these do get reported to us every month. Okay, so just some lab equipment for testing the fluoride residuals. We've got two methods typically in use. So the first is the Spottins. It's a reagent solution. It's based on the reaction between fluoride and a red zirconium dye lake that has been formed with Spottins. So the loss of color resulting from the reaction of fluoride with the dye lake is a function of the fluoride concentration. So, and that fluoride concentration is then measured using a spectrophotometer. Second test method is electrode. So the voltage potential is measured with the specific ion electrode, which has been calibrated with known fluoride standards. So the voltage potential will be proportional to the difference between the fluoride in the electrode and the fluoride in the water. And the electrode method tends to be more accurate than the Spottins method. right, so the results of the fluoride testing must be recorded and reported on the monthly operation reports. This is just an excerpt from one of the MOR sheets showing the specific information that's required. So based on the type of fluoride your system uses, the application columns may be a little bit different. But these three columns are the fluoride application, and then these three columns are the residual analysis. So you'll enter the pounds of full solution that day that you used, and then you can convert to pounds of fluoride ion and what was applied. And then you use your lab equipment to report the daily data in these columns. Let's skip that. That's just a bigger view of the MOR sheet. All right, so just some important fluoride notes. Again, fluoride chemicals must be NSF ANSI standard 60 certified. The optimal recommended level of fluoride is 0.7. Fluoride levels above 2 require a tier 3 public notice, because that is the secondary standard, which again is just based on aesthetic considerations. The maximum contaminant level for fluoride is 4. If you exceed 4, that's a violation notice. I think it's at tier 2 with a tier 2 public notice. And tier 2 is you have 30 days. Well, no, violation notice might be tier 1, but okay. Fluoride, again, must be the fluoride added and the residual readings must be reported on the monthly operation report. Your fluoride levels must also be reported in the consumer confidence report. Any new installation of a fluoride system or upgrades to a system or any switching of the fluoride chemical requires an Act 399 permit. All right, so just wanted to touch on this briefly again. Fluoridation of public water supplies can still be considered a controversial issue. And you may have people come to you with concerns. So just wanted to provide some talking points that you could consider when speaking with concerned residents. So you can say fluoride is proven to strengthen teeth for people of all ages. But please don't say potential harm from fluoride has been greatly distorted. You can say fluoride occurs naturally in the water, as opposed to fluoride as a chemical added to water. Of course, it's always good to feel like you're being heard. So say, I understand your concerns. I had some too until I looked at the issue, but don't say there's nothing to worry about. And then you can say there's a lot of misinformation about fluoride, and then inquire about any specific questions that they might have or want to discuss. But don't trust everything you read on the internet. All right, so I'm going to go through some problems here, and like we've got enough time to go through a few. All right, so example 1. How many gallons of hydrofluorosilicic acid will be required to apply 1 part per million of fluoride to 1 million gallons of water? Assume that 1 gallon of acid weighs 10.4 pounds. So as you're familiar with in the previous two presentations, we want to solve for million pounds of water. So we take our 1 million gallons and we multiply it by the conversion factor of 8.34 pounds per gallon because we want to get to pounds of H2O so that we can input that number into our equation down here. So we need million pounds of H2O. So that gives us 8.34 million pounds of H2O. And then step 2, we solve for the pounds of fluoride, which is we need to solve for the pounds of chemical. We already have the part per million value, which is provided above, which is 1. So in order to solve for pounds of chemical, we're going to multiply the 1 part per million times the 8.34 million pounds of H2O to give us 8.34 pounds of fluoride. So that's the pounds of chemical that we just solved for. And then step 3, we want to solve for the pounds of solution. So we want to convert that pounds of fluoride to pounds of solution. And here's that 19.8% that we discussed earlier. So we have the pounds of fluoride, we have the percent in our solution of fluoride ion, and we need the pounds of solution now. So if we rearrange this equation to solve for pounds of solution, we divide the 8.34 divided by the 19.8% to give us 42.12 pounds of solution, which makes sense because we would expect to need more pounds of solution than pounds of fluoride ion. Okay, to convert the pounds of solution to gallons of solution, we just use the value that was provided with the 10.4. So to convert pounds of solution to gallons, we divide it by 10.4, and we come up with 4.05 gallons of acid solution are needed per 1 million gallons to give us a residual of 1 part per million. All right, example 2. How many gallons of hydrofluorosilicic acid will be required to apply 1 part per million of fluoride to 1 million gallons of water if the natural fluoride concentration is 0.3? So again, we're going to convert our gallons of water to pounds. That's step 1. And step 1, we also determine how much fluoride we need to apply. So we already have 0.3 naturally in our water. So if we want to apply 1 and we already have 3, we subtract 3 and we need to apply a concentration of 0.7 parts per million to our water. Okay. So we have our equation once again. We have parts per million equal to 0.7. We have our million pounds of water calculated, which is the 8.34. If we multiply these two together, we solve for the pounds of chemical, and that gives us 5.84 pounds of fluoride. We use that 19.8% again. We need to find the pounds of solution. So just like example number 1, we divide the pounds of fluoride by the 19.8%, to yield the pounds of solution, which is 29.5. This up here is just another way of writing 79% or 25%, if that's helpful to you. But the main step is to divide pounds of fluoride by the 19.8% to get the pounds of solution. Okay, then we solve for the gallons of solution. Sorry, using the 10.2 that was provided. So 2.89 gallons of solution is required to get a residual of 1 part per million in 1 million gallons of treated water. Okay, example 3. How many gallons of hydrofluorosilicic acid is required if the average pumping rate is 400 gallons per minute for 4 hours? The natural fluoride concentration is 0.4, and the final desired concentration is 1. So the difference in this example is we have a pumping rate instead of a volume that's provided. So we need to convert this pumping rate to a volume. So that'll be step 1. Excuse me. So if we're pumping 400 gallons per minute, we need to convert that to the volume that was produced per day. So we're going to multiply the 400 gallons per minute by 60 minutes per hour. The minutes will cancel. So now we have 400, we have a value that's 400 gallons per hour. We multiply that by the 8.34 conversion factor. And then we convert from 1 million pound unit to 1 million pounds. So the pounds will cancel, the gallons will cancel, the minutes will cancel. And then we'll multiply that by 4 hours, because that's the amount of time that we pumped. If we multiply all of that together, we get 0.8 million pounds of H2O were produced that day. Okay. So if we go back up here, we see that there's a natural fluoride concentration in the water. And we're trying to get a final desired concentration of 1. So we'll subtract the 0.4 from the 1 and to get 0.6. So we need to feed 0.6 parts per million of fluoride at our drinking water plant. Well, that's the desired. It's the what we need to calculate. So that's what we're going to add to the water. All right, so again, we know parts per million, which is 0.6. We know million pounds of H2O, that's 0.8. We multiply those together, that's going to solve for the pounds of chemical. So that results in 0.48 pounds of fluoride is needed. And to get from pounds of fluoride to pounds of solution, again, we divide the pounds of fluoride by the 19.8% to give us 2.42 pounds of solution. And to convert our pounds of solution to gallons of solution, we divide it by 10.2, which was provided in the example. So that gives us 0.237 gallons of solution required. Okay. All right, and the next example. I'm sorry, I can't read the top sentence, but how many will be required for a period of 30 days if the average daily pumping rate is 700 gallons per minute. The natural fluoride concentration is 0.45 milligrams per liter, and the desired fluoride concentration is 0.95. So again, we don't have a volume of water, we have a pumping rate, and we need to convert that to a volume of water. So that's the first step. So 700 gallons per minute is pumped. We multiply that by 60 minutes per hour to cancel our minutes. Then we multiply that by 24 hours per day to cancel our hours. We multiply by our conversion factor of 8.34 to convert from gallons to pounds. So our gallons will cancel out. And then 1 million pounds conversion factor. And then we multiply that by 30 days to come up with our 1,000,000 pounds of water per day, which is 252. So we have a volume of water that's been converted to 1,000,000 pounds. So that's the denominator of our formula. And then if we go back up, our desired fluoride concentration is 0.95. We subtract the natural fluoride in the water, that's 0.45, to get a desired parts per million of 0.5 parts to go into our equation. All right, to get the pounds of fluoride chemical, we multiply the parts per million by the pounds of 1,000,000 pounds of H2O. So multiplying 0.5 by 252, we get 126 pounds of fluoride. All right, we've seen this already, but again, to convert from pounds of fluoride to pounds of solution, we divide the pounds of fluoride by the 19.8%. And that gives us 637 pounds of solution is needed. And then we solve for gallons of solution by using the 10.2. So 637 divided by 10.2 gives us 62.44 gallons of solution. All right, last example. This one's very wordy, but it's actually pretty simple. In this example, we're using sodium fluoride, which is the powder, as opposed to the previous 4 examples, we're using the acid. So that's one of the biggest distinctions in this example. So sodium fluoride is sometimes applied by means of a saturator. In this treatment, excess sodium fluoride is added to the solution container and is applied as a 4% solution, the maximum solubility. The amount of fluoride used can be determined by measuring the number of gallons of the 4% solution used in a given period of time. If the city pumps 480,000 gallons of water per day and 26.4 gallons of 4% pure sodium fluoride solution was used, what was the concentration of the applied fluoride? Okay, so step 1 is finding our 1,000,000 pounds of water. So if I go back up, the city pumps 480,000 gallons of water per day. So that's gallons, and we need to get to 1,000,000 pounds. So 480,000 times our conversion factor. So we're going from gallons to pounds to million pounds. And if we multiply those together, we get 4.003 million pounds of H2O per day is pumped by the plant. All right, step 2, solve for pounds of solution applied. So if I go back up, it says 26.4 gallons of 4% pure sodium fluoride solution was used. So 26.4 gallons of solution was used. And they provide the solution is 8.4 pounds per gallon. So we're not using the 8.34, we're using 8.4. Because this is specific for the chemical solution, not for just water. So the 8.34 is just to be applied to water, converting from gallons to pounds. So we multiply the 26.4 by 8.4 to get 221.76 pounds of solution per day. And then step 3 is to solve for pounds of fluoride applied. So we have 221 pounds of solution. We multiply that by the yield of the sodium fluoride, which we discussed in an earlier slide, which is about 45.2%, times the maximum saturation. So that's that 4%. So we get 4 pounds of fluoride applied that day. So to get the parts per million applied that day, we divide the pounds of fluoride by the million pounds of water to get 1 parts per million applied that day.